were discussing about the causality, the cause and effect relations, and we were discussing the causality of the I element. And we had discussed that we had discussed it with reference to a mechanical quantity, that's a mass. And we had seen that whatever effort is applied to this mass, whatever effort in the sense, whatever force is applied to this mass, so it results in the change in the momentum of the mass, and uh, the inertia element actually just receives this effort, it integrates that effort and determines the momentum associated with it. It is its state, and then it produces an output which is a function of momentum, of the generalized momentum. The output is in the form of flow. So this is the output, and we saw that we could write it mathematically in a form like this, that the flow is corresponding to a function of the integral of the cause. That means the past cause is taken into consideration till the present, and so the causal stroke, it comes here towards the I element in this particular causality. We could also write this as the derivative of the effect, time derivative of the effect is a function of the cause. And this we had discussed is the natural or integral causality for the I element. It's the integral causality because you can see here that there is an integral involved, and it takes into account the past history of the cause. So that's the characteristic of the integral operator, that it keeps a track of the past right up to the present. So this is quite natural and it is understandable, and that's why it's called as natural or integral causality for the I element. And we had also discussed in course of our lecture that we have the causality of the C element, and here if we have the motion of the point A, one end of the spring as VA and the motion of the other end B as VB, the relative velocity can be obtained as VA minus VB. And the rate at which this deformation is taking place, see, the deformation of this spring takes place, that we can write as Q dot, which is the difference of the motion, difference of the velocities of the two ends. So we can take this as the rate of change of generalized displacement. Now coming to the bond graph representation of the C element, I had discussed with you last time that the C element represents compliance. Now since we are considering a spring, the stiffness is the inverse of the compliance. So we'll write a K inverse here. We have an effort which is a function of Q. And you know in your simple mechanics that for a linear spring, the force that is produced is directly proportional to the deformation of the spring. And we have the flow associated with the spring as Q dot, that is the rate of change of the deformation. So these two variables are the variables of power associated with the spring. Now, suppose you you pass in an input which is flow. Input is cause, which is flow. And the spring, what it does is it integrates this cause and it determines its state, which is its generalized displacement. And it produces an output which is a function of this generalized displacement. Its output is effort, and it is a function of the generalized displacement. So what does the spring do? It takes the input, integrates it, determines the state associated with the spring, and then produces an output which is a function of this deformation, which is its state. So this is the input output relationship corresponding to the C element. Now let us look at it from the cause effect point of view mathematically. We can see that we got the integral of the flow, which is actually integral q dot, multiplied that with k, and the integral was from some initial time to the present time t, and that's why we have taken a dummy variable tau, time variable. And this is equal to k into t if the spring is linear. If it is non-linear, then it will be integral of that non-linear function. And this is going to be a function of the generalized displacement q. In this case, it's a linear function. So you get the effort as a function of the generalized displacement. So in this case, the causal stroke is placed here because this end is the end which receives the effort. Okay, so this is the output, effort is the output, so it receives, hence the stroke has to be placed over here. If we write it in the same way as we had done before, we can say effect is a function of the integral of with respect to time. Okay, so this representation is exactly what we have here, and we can say that this is a natural or integral causality for the C element. So what happens is that because of this integral, the spring is able to retain the past history of motion that is provided on its ends, and it integrates that and determines its present deformation and provides an output which is a force. And you can understand this also, you can understand it very well if you take a soft spring. Imagine as a thought experiment that you have a soft spring in your held between your fingertips, let's say between the thumb and the index finger, and let's say it's just a ball pen spring or something like that, a soft one. Now if you apply a deformation to it, let's say 1 centimeter, you deform it, you compress it by 1 centimeter, the tips of your finger, the pads of your finger are going to experience a certain amount of force. Keep that in mind. Now you come to a stage where you're holding between your fingers a harder spring. Let's say it's very hard. And you try to apply the same amount of deformation, that is 1 centimeter. You try to compress it by 1 centimeter. The spring is harder. So what would be the effect that your fingertips would be experiencing? Certainly more force. So you can see that you are able to provide the deformation to the spring, but you are not able to determine its effort. The effort is decided by the spring, by the characteristic of the spring. If it is a soft spring, it will apply less effort. If it is a hard spring, it will apply more effort. So this is the idea of cause and effect. Here, the spring takes in the motion, which is taken as cause. It integrates that, and depending upon its characteristic, depending upon its hardness or softness, it produces an output which is the force that you experience on your fingertips. And that is because the spring decides one variable of power when it receives an input, which is the other variable of. So I hope this idea of causality has integral causality of the spring has become clear to you. The same thing is also true for the I element. In case of the I element, which we considered earlier, you have the causality of the I element like this. I'm just giving you an example to explain to you the idea of causality of the I element. So the characteristic, this causality, for this causality, the constitutive, that's the characteristic of the I element plays a role. So you're applying a force on this I element, on this mass. Let's assume that you have a tennis ball and you're applying a 10 Newton force on it. So the tennis ball will move a certain distance. If you apply the same 10 Newton force to a shot put, okay, which is much heavier, the shot put is not going to move the same distance as moved by the tennis ball. And that is because the mass is much larger. And so although the shot put receives the force applied by you, but it's the shot put which decides the output, that is the motion which it should have. Okay, so this is the idea of cause and effect, that both the effort and the force cannot, and the flow cannot be decided by the same subsystem. So for the I element, you are applying the 10 Newton force on the mass, and the mass is producing the flow. This is the normal understandable causality of the I element. Okay. Let us proceed further towards the next slide. If we look at the causality of the C element in derivative causality, we can see that this spring, if we write its causality, suppose if the input is effort, okay, and the spring has to determine its state, which is the generalized displacement or the deformation in this case, and it has to produce an output effect, which is the derivative of this state. In that case, the relationship will mathematically be this one. Now here you have the derivative of, so the causal stroke will come here. You can see the causal stroke comes here. Now mathematically it means that the effect is a derivative of the function of cause. And this is actually not something which happens in nature, because we know that the cause has to be taken into consideration right up to the present. Now this does not take into account, it doesn't take into consideration the past history of cause. And so this is not a natural form of causality for the C element. It is not a natural form of causality, because it does not, the effect does not depend on past cause up to the present. Okay. So causality of the R element, that's the next point that we will take, next topic. Here we have the R element, and it's an electrical element. So we are going to use the Ohm's law relationship. Let's say we have the ends of the resistance R, ends A and B, and VA and VB being the potentials at the points A and B, the absolute potentials. And we can say that the current that is going to flow through this resistance is equal to VA minus VB divided by R. VA minus VB being the potential drop across this. So this potential divided by R, R is this resistance, and that is equal to effort divided by R, which is a function of the effort. Now, if we write it in terms of bond graph, we can see that here we are having the R element. Now, input to this is just our effort. Now, this effort input, that is the potential difference across A and B, it results in the output of a current. It produces a current in this, which is directly proportional to the potential difference. And this relationship is given by this R. So here we have the effect. So the output force here, the flow, that is the current here, is a function of the input directly. You see here there is no integral or derivative involved. Here it's a direct algebraic kind of relationship where you straight away you provide the effort at this moment of time, and here you have the flow available to you. This instantaneous relationship is the characteristic of the R element. So in this case, in this particular case, input is the voltage potential difference. So here you have the causal stroke placed here, and effort is equal to VA minus VB, which is the potential drop across this, and that is equal to R minus I, R into I. That is R multiplied by flow, which is phi, which is a function of the flow. So the same resistance, but now instead of applying the potential difference across A and B, what you're doing is you're applying a current, you're forcing a current through this. That results in the generation of a potential difference across the ends of A and B. So if you pass a current through A and B, force a current through A and B, it will result in the development of a potential difference across A and B given by this. So this is the other way of looking at it. So if we are to write the causality configuration corresponding to this, now you have the R element, the input to the R element is flow over here, and the R element is going to produce an output which is a function of that flow. So here also you can see that the relationship is linear. It is instantaneous rather. You can see that the end which receives the effort, that is this end, it receives the stroke. It's different from this causality. Okay. Now in simple cases like this, it is possible for us to take R in any causality pattern like this, either like this or like this, depending upon whether you are imposing an effort across it or whether you are imposing a flow through it. In this case, you are imposing an effort across it, and in this case, you are forcing a current through it. So this is the causality for an R element. But an R element can also sometimes, depending upon the phenomena, it can also have just one type of causality and not the other. And that can happen in phenomena of friction. For example, dry friction. So where the relationship between effort and flow is not invertible, and that is where it can happen. It can happen in pneumatics, in several areas where it doesn't. Maybe in our discussion sometime, later discussion sometime, I'll explain about this aspect to you, or possibly I could also explain it to you today. Before we proceed to the transformer, I think we can have a discussion on this aspect. Yeah. I think I did not explain to you about the energy concept of the C element. So let me do that before we proceed towards the R element. But I think we have very less time. Now, here we are going to discuss an exceptional case where we have, let's consider a block which is resting on a surface. Let's say we have a surface and this block is just resting on this surface. And uh, let's say we apply a force on this. So we have a force applied on this. I hope you all of you can see this example. Hello.
Yes, sir.
Okay, fine. So we have this mass here, M. We have this force being applied here, and we know that there will be a frictional force that will be applied uh, between these two. It will result on account of this. So let's represent the frictional force over here. We'll show this like this. So we have the frictional force, say it is given by Fr. And we know that it depends upon the normal reaction. So if you have the weight of this block given by mass multiplied by the acceleration due to gravity, let's consider this mass. So this is the weight, and there's going to be a normal reaction. We know that there will be a normal reaction. In this case, it will in fact just be balanced by this weight. So, so it's going to be corresponding to this. At the same location, I've deliberately taken it slightly shifted towards, just to distinguish. And here, so this is our normal reaction, and this is the weight. And we know that since there is no motion in this direction, this has to be equal in magnitude, but opposite in direction to the weight. So these are vectors, but we'll say that in magnitude, this normal reaction is equal to the weight. Okay. Now, if you apply a force starting from zero, suppose we take a force, we apply a force starting from zero. Um, we are going to apply this force F here on this axis and here FR. So we will see that as we apply the force F, initially there will be no motion of the block, right? So since there is no motion, it means that uh, the resultant of forces in the horizontal direction has to be the same. That means FR has to be the same as F. So you will see that this situation will continue. FR will be equal to F. From here, it's like a 45-degree line, okay, because FR is going to be equal to F till a particular point here. Now, this point is the point of impending motion. This is where motion is just going to start. But up till here, in this entire region, you will see that the velocity of the block that is going to be equal to 0. So this velocity is equal to 0. So we'll take this as velocity of the block. Initially it is at rest, and so in this region velocity is equal to 0. And whatever is the force that is applied is also the same as the force of friction that is experienced. So here you will see that if the force, whatever is the force applied, same as the force here. If you apply so much force here, you will get this frictional force. It's a linear, uh, absolutely linear relationship over here. So far. Now over here you have impending motion. Now here the motion is just going to start, and we know that at this stage there will, if you apply a little more force than this, the frictional force here is suddenly going to fall. This limit we call as the limit of static friction, the force of the static force limit of friction. And usually we write it as Fs is equal to mu n, if you remember your mechanics. Okay, so this is depending upon, well, let's just keep it as Fs, it's our static. Thereafter, the force will suddenly fall and it will come to a stage, let's say over here, or maybe a little lower. Deliberately, I will take it a little lower or a little higher so that it doesn't. Yeah. So let's say it comes here. Suddenly it falls, and then here either it remains constant or it increases depending upon the velocity or whatever nature of friction it may have. So these are the possibilities. We may have over here the velocity. We will have here velocity is not equal to 0. The relative motion between these two surfaces is not equal to 0. So you can see that you got this relationship proceeding like this, and then suddenly it dropped and then either went like this or it went like this. Okay. Now here in this particular case, you are getting a frictional force relationship, which is also a function of the velocity. Certainly it is a function of the velocity as well. Okay, it depends upon the applied force till in this static, but thereafter at this level you are unable to um, determine what should be the force that is to be considered. uh, the moment you are here in this region, okay, now two values are possible. One is this value, okay, the other is this value here. Got it? So you have two values possible. That means this curve is not invertible. This relationship is not invertible. For the same frictional force, you have two possible values of applied forces. So naturally, it's not. It could be at with a velocity, or it could be without when velocity is zero. So this relationship is. This is the case of dry friction. So this is a case where this relationship is not invertible. So it's an example of non-invertible causality relationship. That means the relationship can be in one causal form only. So in this case, you have R, let us say like this. You can impose flow on this, but it will decide the effort. So you may decide the flow, that is the velocity, but it is the R which is going to, depending upon the velocity, it is going to decide what should be the frictional force. So this is flow variable and this is the effort variable. Okay, I think we are running out of time, so we will have a discussion at length if required. If you don't understand what we discussed today, in this particular phenomena, the causal stroke cannot be placed here because you can't invert this relationship. Okay, so we'll stop here for today. If you have any difficulties, please let me know.